Look at a cloud drifting overhead. It appears soft, weightless, and almost empty, like a giant piece of cotton floating through the sky. But that innocent-looking cloud may contain hundreds of thousands of kilograms of water. Some enormous storm clouds can contain far more. So why doesn't all that water immediately crash to the ground? And if clouds really are that heavy, what exactly is holding them up? To solve that mystery, we first need to understand what a cloud actually is. A cloud is not made from water vapor alone. Water vapor is an invisible gas. What we see as a cloud is an enormous collection of tiny liquid water droplets, ice crystals, or both, suspended in the atmosphere. Each droplet forms when invisible water vapor cools and condenses around a microscopic particle floating in the air. That particle might be a tiny piece of dust, sea salt, smoke, or another aerosol. One droplet is almost unimaginably small, but a cloud may contain billions upon billions of them. And when you combine all those droplets, their total mass becomes surprisingly large. Consider an ordinary cumulus cloud, the fluffy white kind you might see on a pleasant afternoon. Imagine that cloud is roughly 1 kilometer long, 1 kilometer wide, and 1 kilometer tall. That gives it a volume of about 1 billion cubic meters. However, most of that enormous volume is still ordinary air. The liquid water is spread extremely thinly throughout it, roughly half a gram in each cubic meter in one commonly used estimate. Half a gram sounds insignificant, but multiply it by 1 billion cubic meters, and you get approximately 500,000 kilograms of water. That is around 500 metric tons. It is comparable to the mass of several large passenger aircraft, all apparently hanging in the sky. But here is where the question becomes slightly misleading. A cloud does not float as one solid, 500-ton object. It is not a giant airborne water tank. That weight is distributed across an enormous volume, with vast distances between the individual microscopic droplets. Imagine taking hundreds of tons of water and dividing it into an almost unbelievable number of tiny pieces, then spreading those pieces across a cubic kilometer of moving air. Each individual droplet still feels gravity. Every one of them is technically trying to fall. But because each droplet is extremely small, it has very little downward momentum, while air resistance has a powerful effect on it. Think about dropping a stone and a tiny piece of dust. The stone falls quickly because its weight easily overcomes the resistance from the air. The dust particle falls so slowly that even a gentle movement of air can carry it upward or sideways. Cloud droplets behave much more like that dust than like raindrops. Many cloud droplets are smaller than 1/10 of a millimeter across. Because they are so tiny, their falling speed can be extremely slow. Air currents inside and around the cloud can easily match or exceed that downward motion. And clouds usually form in places where air is already rising. Warm air near Earth's surface expands, becomes less dense, and rises. As it climbs, the surrounding pressure decreases, allowing the air to expand and cool. Eventually, it may cool enough for water vapor to condense around tiny airborne particles. That is where the visible cloud begins. So while gravity pulls the droplets downward, rising air pushes and carries them upward. The cloud is therefore not sitting motionless in the sky. It exists inside a constantly moving system of air. Tiny droplets are rising, sinking, evaporating, and forming again. From the ground, the cloud may appear calm. Inside it, however, the air can be in continuous motion. But if the droplets are always falling, why doesn't the cloud slowly empty itself? Sometimes it does. Cloud droplets can evaporate before they travel very far. They may also be carried upward again by rising air. For rain to form, the droplets usually need to become much larger. Tiny droplets collide with one another and combine. In colder clouds, ice crystals can grow and interact with supercooled water droplets. As these particles grow, their weight increases much faster than the air resistance acting on them. Eventually, they become too heavy for the surrounding upward air currents to keep suspended. Then they begin falling toward the ground as rain, snow, or another form of precipitation. So rain is not an entire cloud suddenly falling. It is what happens when some of the cloud's microscopic particles grow large enough to escape the moving air supporting them. There's another surprising detail. Clouds are not always lighter than the air around them, simply because they contain water. The cloud exists within a mass of moist air, and that entire parcel can remain buoyant when it is warmer and less dense than the surrounding atmosphere. The visible droplets add weight, but the rising, comparatively buoyant air helps carry them. As that air cools, mixes with its surroundings or stops rising, the cloud may weaken and disappear. Its droplets can evaporate back into invisible water vapor without ever becoming rain. That is why a cloud can form over a mountain, change shape, and then seemingly vanish into clear air. The water did not disappear. It simply changed from visible droplets back into invisible gas. And this explains why the question, how does a cloud float, has more than one answer. A cloud stays in the sky because its water is divided into countless microscopic droplets. Those droplets fall extremely slowly because air resistance is strong compared with their tiny weight. And the cloud usually exists inside rising and turbulent air that continuously carries those droplets. In other words, the cloud's enormous total weight matters less than the size and behavior of each individual droplet. A ship weighing thousands of tons sinks if it fills with water, yet it floats when its mass is spread across a shape that displaces enough water. A cloud follows a different principle, but the lesson is similar. Mass alone does not tell you what something will do. Its shape, density, environment, and how that mass is distributed matter just as much. So the next time you see a fluffy cloud drifting peacefully overhead, remember what you're actually looking at. It may contain hundreds of tons of water. Every droplet is being pulled toward Earth, yet each one is so small, and the air around it so active that the entire cloud can remain suspended above you, at least until those tiny droplets join together, grow heavy enough, and finally fall as rain.